right, so we are going to continue with some substitution with definite integrals. We did a couple of examples last time. We saw really one of each of these methods. One is that you kind of treat it like you do an indefinite integral. You get all the way back to this point where normally with an indefinite integral you just tack on a plus c, right? So if you were to kind of scroll back up and look at some of our indefinite integrals, you substitute, you get in terms of u, you integrate, and then you go back to x's, and then you just say plus c. So with a definite integral, rather than going all the way to the point, we don't say plus c, but we take it all the way to the point where we go back to x's, and method 1 then just says evaluate between what are these x limits of integration. Just like you learned initially with your definite integrals in the fundamental theorem of calculus. The other method says, well, we don't need to do that. As long as we're taking everything, the whole integrand, all the functions of x, the dx, as long as we're moving all that over into u's, why not just change these x limits into u limits as well? So that's the other way, and then you never need to go back to x's. The important thing is that you don't mix up the two, right? So you don't want to, what's probably the most common error would be to stay in terms of u's, but then evaluate between the x limits of integration, right? So those are the things that you want to be careful of. So let's just continue. We'll look at maybe another example while we continue to really build on to our u-substitution ideas. So we're just continuing to always see new examples when it comes to u-substitution. All right, so let's take a look at another definite integral here. And this time I'm just going to say evaluate, and we'll figure out which method we're going to evaluate with. So maybe I evaluate the definite integral from -4 to -1 of x times the square root of x plus 5 dx. All right, so this kind of takes us back when we look at all the different kinds of u's we've had with u substitutions. The last one we just kind of was a first time for us was in number 2 up above, whenever we have a natural log function, because that doesn't even need to look like an inside. That is going to be a choice for you because that's something that we don't even know what its antiderivative is, so we have to get rid of it. So that was something a little bit new. This number 3, we're kind of back to something that I would say is more like our first examples, in the sense that we have, I guess, what I would call a more obvious inside. So it looks like we have a u here that is underneath of a power or inside of a radical. We have u equals x plus 5. All right, so then we take our differential. So our du in this case, well, that's just 1. So du equals dx, 1 dx. And so now when I look back at the original function, all I have is all I have in my differential is du equals dx. But back in the original integral, I still have an extra x. And it is important to realize that this is a problem. So whenever you catch yourself writing, like if you were to write, some kind of, and yeah, this one's a definite integral, but if you were to write x times the square root of u du, this makes no mathematical sense. Okay, so this right here, we can't do, right? This is a problem. So this, I'll just write this way. What's the main problem is that we still have a function of x here, that little old x. We have to get all of the x's and dx's into u's and du's. So in this case, we're going to again see something a little different than anything we've seen before. Oops, I didn't mean to erase that. And we're going to kind of look back at the original integral. So far, when this has happened, it's typically been a situation where maybe I didn't make the right choice for u. But if I look back, I don't really see any other reasonable choice for u. I don't see a denominator in any way. I don't see like the natural log function. There's nothing with like these trig functions or anything that we've learned. So here's what I want us to think about. I want us to think over here in this area with the problem. I want us to think about how we could get rid of that problem. So how could I get rid of, let me even highlight that, how can I get rid of that x and get it in terms of u? Well, in class we'd let you think about it, and it doesn't take too long before somebody typically kind of goes back and takes a look at that u equation to say, well, if u is x plus 5, that tells me something else. So this right here also tells me that's true if and only if u minus 5 is equal to x. So in fact, that problem that we just had, I think we can take care of that if we replace x with a u minus 5. So that is exactly what we're going to do here. So we're going to kind of build off of what initially seemed like a big old problem there. And so now let's see what that does for us. We're going to have in place of in place of x, we're now going to have u minus 5. So that is our replacement for that lingering x. Okay, but we still have, of course, our u to the, let's go ahead and replace that with our square root there, with the 1/2 power. And so what do we have here? So we have, there was our u and our du. All right. So initially this isn't yet perfect because I still do have a product here, and we can't integrate a product factor by factor, but this situation is something that I can go back to just my basic antiderivative ideas and basic indefinite integrals or definite integrals integration, and I can distribute. So I can take care of this situation relatively easily. So if I distribute, I'm going to have u to the 3/2 minus 5u to the 1/2. Okay, so that looks pretty good. And I would say we are ready for integration here. We're ready to take that antiderivative. So this is going to be, just using our power rules here, we're going to have our u to the 5/2, so adding 1, and then divided by that 5/2 is multiplying by the reciprocal of 2/5. And then we're going to have minus, and that 5 gets carried along as a constant multiple. And then we're going to have the u to the 1/2 or 3/2 divided by 3/2 is like multiplying by 2/3. And so at this point, this is really where, we kind of have the option, right? So whether or not you want to kind of look at this with a method 1 idea, or if you want to look at this with a method 2 idea. So if you're going to do method 1, so maybe I'll just do both of them in this case. So if you were going to use method 1, and so I generally will be giving you the choice. Maybe in future semesters you might have an instructor that really prefers one versus the other. So method 1 says you kind of just keep going all the way back to your x's, just like you typically would if you were taking an indefinite integral. So we're replacing our u's with the quantities of x plus 5 binomials. And so I've replaced those, and instead of a plus c, I now would evaluate between my x limits of integration. So the original x limits of integration here are now what I can put back in those little boxes that I had kind of left there before. Okay, so these are our original x limits of integration. So the limits of integration in terms of the variable have to match what the function variable is. X limits of integration if you're in functions of x. Okay, so the other option, of course, would be to say, no, I think I'm going to do method 2. And if you were doing method 2, honestly, you probably would have written it right up above at that step, but I'm writing out both the steps, so we're going to write them out separately here. So with method 2, you're leaving everything right? So this is where I'm saying if you were doing method 2, you would have written those right up above there. All right, but the difference is you're now going to change over into u limits of integration. All right, well, that's going to tell me that I had my u here. The rule was that u was equal to x plus 5. So on the first one, -1 plus 5 tells me my upper limit of integration is going to be 4. And then my lower limit of integration, again, u is equal to x plus 5, so -4 plus 5. And so this tells me that my lower limit of integration is going to be 1. Okay, so those are my upper and lower limits. And so if I look at it here, I end up with subbing in, I have my 2/5, and 5/2 is like a square root to the 5th, so square root of 4 is 2. 2 to the 5th would be like a 32 there. And then minus 10/3, subbing in 4, square root of 4 is 2, 2 cubed is 8. So that's subbing in my upper limit of integration minus my lower limit of integration. That's going to be a lot easier, just 2/5 minus 10/3. All right, and then we can continue and get what that would be. If I'm doing my x's, it's the same thing. It's just that this is the place where you end up doing your u's, right? So you sub the -1 in, and what we already did with the u's, you're going to have 5 minus 1, and you're going to get to 4. So maybe, I don't know, maybe does it require like a smidge more at this step? I suppose, but typically those u's are easy to compute. So maybe I'll just say, okay, then that would have been like 4 to the 5/2 minus 10/3 times 4 to the 3/2. Maybe I have to do just a slight bit more of writing out of my work at this point. And then again, 2/5 times, and then 5 minus 4. Oh yeah, that would have been 1 that I would have had here to the 5/2, and then minus 10/3 times 1 to the, where am I at, 3/2 here, you know, something like that. But either way, that's going to then just take you right down to, at this point, of course, we're at the exact same point. Okay, right? So either way, you're getting to the same exact result here. And so if you sub this into your calculator, this would have come out to be approximately, well, actually I had the fraction too. So this would have come out to be, this would have been -165 over 15. And then that is approximately -10.9. Actually, no, it's exact because I have my 3 repeated. All right, so that's how that one would work out. So this was kind of a recap of the 2 different methods of u-substitution with definite integrals, but also a new type of u-sub. And so I wouldn't say a new type, but this new step where sometimes if you have a lingering x and you have a pretty basic u formula, you might be able to make this additional substitution for a lingering x. And the key is, does that make it better? Because sometimes we do that and we get to an integral. This one, it just required a little bit of distributing up here at this step that I just accidentally erased, like I tend to do here. It just required a little bit of distributing at that point. But sometimes you get to something where you get an integral and it actually wasn't even something that was any easier. Like you do all these things, you get it in terms of u, and you still can't integrate it. You know, this is, again, integration is a little bit more of an art form. It's not like taking derivatives where it's just simply following